I'll be talking about the octopus's visual system, explaining its function and comparing it to the human eye. In a process of convergent evolution, octopuses developed a camera-type eye similar to humans, despite evolving in drastically different environments. As you can see on the diagram on the right, one of the striking differences is that the octopus eye lacks the blind spot that human eyes have. Unlike human and other vertebrate eyes, where the retinal axons pass over the retina to join the optic nerve, in octopus eyes, these axons pass behind the retina, leaving its light-receiving surface unobstructed. Unlike the human eye, where the shape of the flexible lens is changed to focus at different distances, the eye of an octopus focuses instead by moving the stiff lens back and forth like a camera or a telescope. This lens translation is accomplished by ciliary muscles, which are also present in the human eye. The octopus eye in its relaxed state has a range of about 8 feet or 2.5 meters. The lens is moved closer to the retina to focus on more distant objects. This is because light from distant objects needs less refraction or bending than light from closer sources. Moving the light closer to the retina prevents light from converging too soon and making the octopus myopic. An octopus has separate motor and focus control neurons for each eye, allowing it to move and focus on objects independently. While this is not great for binocularity, which relies on overlapping visual fields, it does give them an excellent field of view, with each eye having around 80 degrees of freedom of movement. Octopus photoreceptors are arranged in a regular orthogonal pattern, unlike the semi-random layout of human photoreceptors. This gives octopuses sensitivity to different polarizations of light, allowing them to get meaningful information from polarized light that the human system would just interpret as glare, like the reflection of the sky in the image on the left, and the same image on the right with the glare filtered out. This ability lets them defeat certain forms of visual camouflage used by other sea life, such as a silver-scaled fish using bright polarized reflection of daylight to confuse predators, or fishes that are transparent. The octopus can spot them because their bodies are still polarizing light. Since the photoreceptors of an octopus are directional, they do rely on structures called statocysts to reflexively keep their pupils in a constant horizontal orientation, regardless of the body's position. These statocysts are analogous to human inner ears, which sense acceleration and help us maintain balance. Some octopus species contain only rhodopsin, which is color insensitive. But despite having only one photopigment, octopuses are able to distinguish between colors using chromatic aberration. Their rectangular or even W-shaped pupils, sometimes, as you can see, have evolved to maximize chromatic aberration, which is when white light splits into its constituent colors because of differential refraction in different parts of the lens. Each color lands on a particular part of the octopus's retina, giving them a unique type of color perception. In addition to the eyes, octopus skin is also an active part of the visual system. It contains chromatophores which contain a photopigment very similar to the rhodopsin in the retina. The skin's light sensitivity could help them discriminate between bright and dark environments, helping guide the color of their camouflage. Putting together what we know, an octopus's visual world likely has a wide, near 360-degree field of view, although vision acuity is likely low because of the intentional chromatic aberration introduced by its pupils. Bright, polarized light, which would be blinding or just glare to us, carries information that is indecipherable to creatures with a random layout of photoreceptors in the retina. Different colors would map to particular locations on the retina, like objects in our field of view would for us. This idea of color being perceived as locations in the visual field is probably the hardest aspect to visualize for me. As to the photosensitive skin, I'd imagine it to feel like the warmth of sunlight on our human skin, but with more granularity. That concludes the presentation. Thank you for watching.